I want to walk through a basic stoichiometry problem. Um, these are the types of questions that really constitute the backbone of chemistry. 3.2 grams of propane are burned. How much water is made? First, hopefully you recognize that you have to have a balanced chemical reaction. In this class so far, you shouldn't have to know what propane is, but propane is a 3-carbon hydrocarbon. So it's a saturated hydrocarbon, which means every carbon-carbon bond is a single bond, and all the carbons are full of hydrogens. Carbon wants 4 bonds, hydrogen wants 1. This is the structure of propane. Of course, it's unrealistic because I drew it in the plane of the paper. This would be a 3-dimensional structure with each of these carbons having a tetrahedral geometry, making the bond angle something like 109 degrees, not 90 or less than 90, as you can see here. All right, great. There are 3 carbons and 6, 7, 8 hydrogens. And we need a balanced chemical reaction. I'm going to try to fit this whole problem onto one page. I hope I don't write too small. C3H8, this is combustion. In a combustion reaction, we have to have oxygen. We hopefully remember that oxygen is a diatomic gas. Propane can be a liquid. When we burn it, it's a gas. In general, liquids don't burn. It's the vapor of the liquids which burn. And so propane has to evaporate and become a gas to become combustible. Oxygen, in this context, is also a gas. This is going to create combustion, produces carbon dioxide. I'm going to leave a space here because I know a number is coming there. Carbon dioxide and water. Hopefully we're getting comfortable with balancing chemical reactions. We recognize that this carbon here, the only carbon over here is there. So if I have a 1 here, then I need a 3 there to balance out the total numbers of carbons. If I have a 1 here, I need a 4 there to get 8 hydrogens. Again, if that's not comfortable, let me know and I'll make another video about balancing chemical reactions. So I'm not going to do that here. But then the point is I can only have even numbers of oxygens. If I have 3 here, that's going to be 6. If I have 4 there, that's going to be 4. That's an even number. I can go ahead and run with it. So I'm going to put a 1 there. That 1 doesn't really have to be there. I'm going to put it there anyways. That makes 3 carbons. So I'm going to put a 3 here, which makes 4 waters. And then that is 4 and that is 6. That's a total of 10 oxygens. So I need a 5 here. Perfect. Now, I'm told I have 3.2 grams of propane. 3.2 grams. Grams alone in this class is no longer a unit. In physics, we can have grams. In chemistry, we have grams of something. We often abbreviate in chemistry. I don't really want to write this over and over again. I don't want to write propane over and over again. I'm just going to write pro. In this problem that works, I'm going to divide that by 1. I know another fraction is coming. I'm just going to go ahead and draw that line. I know on the bottom of this fraction is grams of propane. I know that this balanced chemical reaction relates ratios, and the ratios we use in chemistry are moles. If I had 1 molecule of propane, I would need 5 molecules of oxygen, and it would produce 3 molecules of carbon and 4 molecules of water. But that's a really silly way of thinking about it because molecules are so small. I mean, it's easier to say if I have 1 mole of propane, That's a significant amount of propane. If it was a gas, it'd be a big balloon full of gas. It's something I can think about. It's a useful amount. We're better off in moles. And because Avogadro did this really intelligent thing, when I look at this table, I know what a mole of carbon weighs. A mole of carbon weighs 12.01 grams. Here I can be intelligent and say, look, I only have two significant figures here. This isn't going to produce something where I have to be incredibly accurate, but I can come over here and I do need to know the molecular mass, sorry I misspelled that, I don't really care, of propane. And so I have 3 times the mass of carbon, which is 12.01. I'll call it 12.0. We'll keep 3 sig figs. And this is carbon. And then I got to account for the hydrogens, which is 1.00. Again, I'll keep 3 sig figs. It's not going to really matter in a second because they're going to go away, some of that. But in a propane, I have 8 hydrogens, so I'm going to have 8 times 1.01. And I multiply that all out, and I realize when I add, this sig fig's going to go away anyways, but I guess it would round up to a 1. You can go through that if you want. This is 36 plus 8 is 44. 44.01, including sig figs. That has units. This is grams of propane in 1 mole of propane, because that's what these were. This is grams of carbon in 1 mole of carbon. This is grams of hydrogen in 1 mole of hydrogen. And so when we add it all up, we get grams of propane in 1 mole of propane. Again, this is equal to 1 because they're the same thing. 44 grams of propane is 1 mole of propane. I'm going to come over to here. Again, I'm going to shorten this down to 3 sig figs because I only got 2 there. Why does it really matter? 44.0 grams of propane per 1 mole of propane. And we see the grams of propane cancel. I know my next fraction in this is going to be grams of propane on the bottom and moles of propane. Oh, sorry, I'm nice. That was the last one. And I'm going to let that be messy. I'm going to have on the bottom of this fraction moles of propane. And this is where I have to start being intelligent because the question asks how much water is produced. I need to get away from propane, and that was the point of changing grams of propane into moles of propane, because I know that I can turn moles of propane into moles of water. And if I look up here, I say, all right, for every 1 mole of propane, I'm going to end up with 4 moles of water. And so that's just a stoichiometric ratio. These numbers here are called stoichiometric coefficients. And so stoichiometry perhaps isn't as scary as it sounds. Moles of propane is going away. I'm now left with moles of water. So if I just did the math here, I would produce how many moles of water I had created by burning 3.2 grams of propane. The problem with that is that I cannot measure moles of water. And so what I can do is I can multiply by another fraction where I'm going to get rid of moles of water and replace it with grams of water. And doing some basic math, again, oxygen is 16 grams per mole. Hydrogen is 1 gram per mole. So water is 18.0 grams per 1 mole. And if I now look at my units, it becomes clear the answer to this problem is going to be grams of water. All the stuff on the top multiplies together, so it's 3.2 times 4 times 18.0 divided by 44.0 times 1 times 1 times 1. We can obviously leave all the ones out. And this now equals, again, I would just use my calculator, 3.2 times 4 times 18 divided by 44. Enter. 5.23636. I'm obviously not writing all that down. I have to be a little careful. This has 2 sig figs. This is where we started. Mole ratios are infinite sig figs. There is exactly 4.000000000 moles of water for every 1.0000000 mole of propane burned forever and ever and ever. So this 4 is not going to limit my sig figs. It's going to be limited right there. And so I want to round that to 2 sig figs, 5.2 grams of water. It is important to stop now. There is a high probability of mistakes when we do things like this, especially when it's new. I say 5.2 grams of water. Does that even make sense? Well, it does make sense. Grams propane. I track my units. That's how much a propane weighs. That makes sense. It does make sense that I produced 4 moles of water because there's 8 hydrogens in a propane, 2 hydrogens in a water. That's 4 times as much. That makes sense. And I know the mass of water is 18 grams per mole. And then I don't think I made a mistake with my calculator. I like this calculator because I can check that. Then the next logical question is, I started off with 3.2 grams of propane and ended up with more water than the propane I started with. Well, that also makes sense because here the propane is gathering oxygen from the air. We're not talking about the mass of propane. The mass of propane and oxygen together have to equal the mass of carbon and water together. And most of the mass in this reaction comes from the air. So it does make sense that I can end up with more water than propane I started with. I will add something that is required in this class to know is that for this balanced chemical reaction to be complete, I should have put that it's producing carbon dioxide as a gas and water is a vapor, which is also a gas. You would need a delta over this arrow and a delta here. Both these deltas mean heat, but they're very different heat. This delta says the reaction will not happen unless I add heat. So propane and oxygen are not going to start burning unless I light it on fire. This delta says that if propane and oxygen do burn, they produce a lot of fire. So this is just a spark, and this is the fire from propane burning. I often say that this delta shows that propane is safe, meaning that it won't burn unless we light it on fire. And this delta says that propane is dangerous. If it gets lit on fire, it will burn. Safe, dangerous.